So now we're going to look at naming of binary compounds in a general sense. So binary compounds are just those compounds formed between two elements. And we've seen that those two elements for an ionic compound will be a metal and a non-metal. We're going to have to also figure out how we're going to name those molecular compounds that we talked about way back in section 3.3. So binary ionic compounds contain one monatomic cation, that just means a single atom that has lost some electrons, and one monatomic anion, that's just a single atom that has gained some electrons. So we've looked at this exact slide before, and so their formulas just contain one metal and one non-metal. One metal, one non-metal, one metal, one non-metal, one metal, one non-metal. Really simple. Now, how do we name these types of binary compounds? We name them by giving the name of the cation first, follow that with the name of the anion, and then you drop all occurrences of the word ion. So this guy is composed of iron 2 ions, so Fe2+, and also oxide ions O2-. You can see why they combine 1 to 1. So when it comes time to name the whole compound, we just call it ion 2, the name of the cation without the word ion on the end, oxide. Okay, so we've seen this before. It was just a brief review. So that it's not too bad. The big thing here is just deciding whether your compound's name is going to need Roman numerals following the name for the cation. That's your big thing, and we have some rules about that. It needs those Roman numerals if you have a variable charged cation. Now, if the binary ionic compound, as I mentioned, contains a fixed charged cation, Roman numerals are not needed in its name. So this is a really kind of important thing. People want to just give Roman numerals for everything. But if I have the formula MgBr2, I understand that I've got magnesium ions and bromide ions. Now, how did I come up with the name of the anion? Well, bromine has the stem name BROM, and there's a table with the common stem names in them in your book, and then we take the stem name of the anion and then we just add the letters IDE to the end, so we call that the bromide ion. Now I know that it is -1 because bromine is in group 7A, and we take the group number and we -8 to get the charge on anions. Now magnesium is a representative element. It's in an A group. It's in fact group 2A, and for the representative metals we know that the charge is always equal to the group number, and we also know that those guys are fixed charge. They only form one ion. So this guy is going to form a +2 ion. Because it's fixed charge, we just name it as magnesium ion. So to name the compound, what did I say? We just put the name of the cation first, follow it up with the name of the anion. So MgBr2 just becomes magnesium bromide. Now, if your binary ionic compound contains a variable charged cation, then Roman numerals are needed in the name. So FeBr3, I look at the cation and I kind of groan a little. I go, ugh. It's a transition metal and it's not a special case. So I immediately know that it's going to need Roman numerals. Remember that the special cases for the transition metals were those three, and you can remember them. They're all touching on the periodic table. So naming the anion is pretty straightforward. It's the same as what we saw before. Bromine has the stem name BROM. Remember that's in the table 6.2. And there we go. So we can look those stem names up. Maybe you can take a photo of it and save it as a PDF and paste it into your computer. And then we're going to add the ending IDE because that's how we name anions. So it becomes the bromide ion. Now we know the charge on this guy is -1, again, because it's in group 7. And for anions, the charge is equal to the group number -8. So that gives me -1. All right, so I know the charge on my anion. The whole thing that I'm trying to do here is figure out what my Roman numerals are going to be. Because I've got 3 bromide ions, I know that the total charge from my anions is -3. So that means that the charge on my cation must be 3+, because I only have one cation and its charge has to add up to +3. So the cation must be Fe3+, and this has the name iron 3 ion. So there's a little bit of a trick here. You are probably wondering why I always look at the anion first, and the reason is we always know the charge of the anion from the position in the periodic table. There are no variable charged anions, only variable charged cations. So if I can figure out the charge on my anion, then I can always figure out the charge on my cation. And so that's the strategy that you should use. Whenever you've got one of these variable charged things, you can figure out the charge by looking at the anion first. So I've identified that this is the Fe3+ ion, and so that has the name iron 3 ion. So when it comes time to name this compound, we put the name of the cation followed by the name of the anion. So this guy becomes iron 3 bromide. So that's naming the ionic compounds in great depth. We kind of went through that before, but just sort of looking at the two scenarios there, one with a fixed charged cation and one with a variable charged cation. So the other big class of binary compounds are binary molecular compounds. These are compounds which contain 2 nonmetals, and we looked in an Alex topic previously about how to identify these. So this is a binary molecular compound, 2 nonmetals, 1, 2. This also is a binary molecular compound, 2 nonmetals, and so forth. All right, 2 different nonmetals in each case. You want to be able to distinguish this from a binary ionic compound, which is a compound which contains a cation formed by a metal, and then an anion, which is formed by a nonmetal. So you can tell that you've got an ionic compound because it's going to begin with a metal. All right, so that's just really about distinguishing the two. Again, we'd previously seen that, but now we want to learn how to name these binary molecular compounds. So the first thing is we're going to start with the formula and learn how to write the formulas correctly. And we've already done this. Again, this is repetition. We saw this back in chapter 3. So when you write the formula for a binary molecular compound, the atoms are written in approximate order of what we call increasing metallic character. And if you remember that the metals are on the left of the periodic table and the nonmetals are on the right. And in particular, we have some nonmetals tend to linger down the bottom of the periodic table, right? So we have things like lead and tin and bismuth at the bottom of the periodic table. So what we're going to say is that metallic character kind of increases from the bottom left to the top right. Okay, you're going to find your metals in here and then your nonmetals in the other part of the periodic table. So what does this mean for us? Well, remember that 1A is over here and 8A is over there. And then the periods go down here. Okay, it means that you're going to put lower group numbers first. Now, occasionally you get the scenario, say you have like oxygen and sulfur. They're both in group 6A, where the elements are in the same group. If that's the case, you're going to write the one that comes lower down in the group first because it's going to have more metallic character. So they go in order of group, left to right in the formula, but the ones that, if they are in the same group, the ones that are lower in that group will come first. Okay, no problem. Now, there's one little tiny exception, and we have talked about this previously, and it's the exception for hydrogen. Hydrogen is kind of weird. It only has one electron. It's put over in group 1A with a bunch of metals, but it's a non-metal. It can form a cation and it can form an anion depending on what it's being reacted with. So hydrogen is weird, right? And so we have a special rule for hydrogen that says that hydrogen is placed at the end of a formula, but before elements from group 6A and 7A. So here's your kind of like, order for your most common non-metals that are going to be found in these binary molecular compounds. Those that are in group 3A will come first, followed by those in group 4A, and in the order from the bottom of the group up. So silicon and then carbon. In group 5A, again, we're going to the non-metals from the bottom of the group up. So it's going to go antimony, arsenic, phosphorus, nitrogen. Then before we leap into 6A, we're going to put hydrogen. And then from 6A, we're going to go from the bottom of the group up. So tellurium, selenium, sulfur, oxygen. And then finally for 7A, again, we're going to go from the bottom of the group up, iodine, bromine, chlorine, fluorine. We're not worrying about astatine, it's radioactive. So this is going to be our order of the most common non-metals when we're writing formulas, okay? So lowest group number first. If they're in the same group, the one that's lower in the group comes first, and then hydrogen comes last, except for it becomes before elements from group 6A and 7A. And the elements that are in group 8A tend not to form compounds. They're what we call the noble gases. So that's the formulas. When we've got a formula, can we turn it into a name? Now, we're only looking at binary covalent compounds, so we only ever have to worry about the names of two things. And the first one is really easy. We just give the name of the first element unaltered. Simple. And then we give the name of the second element, but we give the stem name or the root name followed by IDE. So just like naming an anion, right? Just like naming an anion. And remember, there's a table of these. These are sometimes called stem names or sometimes called root names. But there's a table of those stem names, so you can always look that up in your book. Okay, and then there's a third step. Greek prefixes are used to indicate the number of atoms of each element. So we should review the Greek prefixes. So the Greek prefixes, and you should know them up to 10. There's a table in your book, so you can just look these up, but ultimately you're going to end up probably memorizing them. So 1 through 10, it goes mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You don't want to confuse these with the Latin prefixes. So mono or 1 in Latin is like uni, 2 in Latin is bi, 4 in Latin is quad. You've probably heard some of these before, right? So be aware that we're using the ones that are derived from ancient Greek. So I always say, memorizing these is not a total waste of time. You can impress friends at parties. I just drank a hexapack. Sounds way more sophisticated than I drank a 6-pack. Okay, so there are, of course, a little exception or two. If there's one of the first element, you don't give it a prefix. So we say carbon disulfide, not monocarbon disulfide. We say carbon dioxide, not monocarbon dioxide. We say carbon monoxide, not monocarbon monoxide. We say phosphorus pentachloride, not monophosphorus pentachloride, and so forth, right? And you can see that the formula and the name have the same sequence of elements, so that's kind of nice. All right, remember the sequence is increasing metallic character like that, which means lowest group number, and if they are in the same group, the higher period. okay, because the metals are like on the left of the periodic table, and if there are any metals over here, they're down the bottom, so that's why we say that they increases along that way. All right, now here we go. If hydrogen is the first non-metal listed in the formula name of the compound, name it as though your compound is an ionic compound. So you don't use any Greek prefixes is all that means. So we don't say hydrogen monochloride, we just say hydrogen chloride. We don't say hydrogen monofluoride, we just say hydrogen fluoride. We don't say hydrogen or dihydrogen sulfide, we just say hydrogen sulfide. So if your compound begins with hydrogen, you want to omit your prefixes, okay? And that's it. All right. So, whoa. We just kind of lost our screen there for a moment, didn't we? So if hydrogen is your first element in your compound, omit. Okay, so now we're just going to look at naming some binary covalent compounds. So there are a couple of things that you want to have handy when you're tackling these kinds of problems. Covalent compounds is just another way of saying a molecular compound. So those terms are used interchangeably, so it just means molecular. And so when we name the molecular compounds, we really want two pieces of information. We want a list of common stem names, and then we want our Greek numerical prefixes. So it was told to me that these are molecular or covalent compounds, so I don't have to worry about ions or anything like that. So in this problem, it says that for compounds containing hydrogen, you may give the common name instead. So I'm just going to scan my list here and see if I can see any that contain hydrogen, and it's this one at the bottom, and H2O. Hopefully you all know the common name is water. So let's look at the top one there. We've got SES2. So we need the name of the first element unaltered, and then the name of the second element. We're going to take the stem name, which is sulf, and change the ending to IDE. So this is going to be sulfide. And then we have to give prefixes to indicate the number of each type of atom in the formula. Remember, we don't use mono for the first atom, so we don't need anything there. And then we have two sulfurs, so our prefix must be di. So this guy is going to be selenium disulfide. Okay. Now, our second compound, the first element is xenon. We give the name of the first element unaltered. And then our second element, we take the stem name and we change it to IDE. So this is oxygen, and the stem name is ox. And then we've got to change the ending to IDE. Now, we only have one xenon, so we don't need a mono for the first atom. And then we've got three of the oxygen, so our prefix will be tri. So this is xenon trioxide. We would expect this compound to be very rare because it contains a noble gas, and compounds of noble gases are pretty few and far between. Noble gases in general tend to be very unreactive. Xenon is one of the few examples it forms a small number of compounds. Okay, XeF6. So xenon, the name of the first element unaltered. The second element is fluorine. We take the stem name, FLUOR, change the ending to IDE. And then now we need prefixes. If you've got one of the first, you don't need a mono. But then we've got 6 fluorines, so it's going to be hexa. So xenon hexa fluoride. Okay, something other than one of the first element, getting kind of interesting. So what have we got here? Our first element is selenium, unchanged. Our second element is sulfur. We have to take the stem name, SULF and change the ending to IDE. Now we add our prefixes. There are 4 of each, so we're going to use the prefix tetra. So this is going to be tetraselenium, tetrasulfide. Now notice that for molecular compounds, we don't simplify the ratio of atom types, right? You don't write that as SES. That is wrong. That's not a rule for molecular compounds to simplify the ratio of atom types. That only applies to ionic compounds. Okay, so now of course we have to do the other class of compounds. We've got to name binary ionic compounds. So you need 2 things to name binary ionic compounds. You want a list of stem names, and then you want to know your charges of your ions that are fixed charges that you can kind of figure out, right? Now the reason for knowing whether your atom is a fixed charged or variable charged atom is because it's going to affect how you name the cation. So the first column here is asking you to write the empirical formula for the ionic compound formed. And this is real easy in this case, because if we look here, every cation is the cesium plus cation, and then the anion always has a -1. So what this means is that these guys are always going to combine in a 1-to-1 ratio, doesn't it, right? If you have equal and opposite charges, they always combine 1-to-1. So this is just going to be CSI, CSF, CSBr, CSCl. So nice and simple, no crossover, nothing fancy. Now, the question is what is the name of the compound? So to write the name of the compound for an ionic compound, we give the name of the cation followed by the name of the anion. So the cation in this case is just the, we give the name of the atom that it's formed from, cesium, and then we have to decide, do we need Roman numerals to indicate the charge? And as cesium is in group 1A, no Roman numerals are needed. Now to name the anion, we take the stem name of the element, which in the first one there is going to be IOD, and we change the ending up to IDE. So this just becomes cesium iodide. There we go. Now for our next one, what is it going to be? Cesium. Fluorine has stem name fluor, and then we change the ending to IDE. So cesium fluoride. There we go. Our next one, still cesium, combined with the anion formed by bromine. The stem name for bromine, BROM, and then change the ending to -ide. Now you're seeing for the ionic compounds, we never use Greek prefixes. That's really important. Never use Greek prefixes for ionic compounds. Chlorine has stem name chlor. There it is. And then change the ending to IDE. Cesium chloride. Okay, not too bad. So we just learned how to name molecular, or what are also referred to as covalent compounds, and now we're naming ionic compounds. Okay, not too bad. Let me know if you have any trouble with that. There's a worksheet where you can practice that I'm going to post online, and yeah, good luck with everything. Relatively straightforward if you just follow the procedures described. Your prefixes.